Hello, everybody. Sorry I can't be there today. Got some sick family members, so I'm home taking care of them and doing some things. But you've got this nice video, so please watch the video, follow along, do what I ask, and it should be a pretty smooth day. By the end, when the video is over, I'll have a nice computer simulation activity for you to do that's inside the study guide. I'll give you the instructions for that, and it should be pretty smooth sailing, honestly. I've done this before and it seems to work really well. So let me share my screen and let's begin. You're going to want your study guides, and we're going to begin on it's the page after the chemistry A review. So I think it's page 5, if I'm not mistaken. I have the slide later that we'll check for sure, but I'm pretty sure it's page 5. But I wanted to start really quick with our learning intentions. Today, we want to make sure that we observe how the model of the atom has changed over time. And then we will, in the computer simulation activity, will identify the building blocks of atoms. So as a little introduction, I like the Mythbusters, and you'll see lots of Mythbusters clips throughout chemistry. And if you ever take physics, you'll probably see even more of them. But I wanted to start with one of the most outlandish, unnecessary Mythbusters moments in this quick video here.
Rockets to find out if any circumstances it's possible to pancake a compact so much you lose it in the wreckage of a 2-truck collision. And to do it, New Mexico Tech has lent them their straight-track rocket roller coaster.
Spell out for you exactly how this is going to break down. When we push the launch button from the bunker, this back sled fires, pushing this front sled down the track to here, where the front sled's rockets kick into gear and carry it the rest of the way down the track. By the time our sled reaches the end of the track here, it ought to be going 700 miles an hour. It will then leave the track, traveling across 20 feet of open space, where it will eventually hit our car. It's back on the nose. Now, the car's backed up against that steel plate and that concrete block, and should simulate our 2-truck impact at the speed of sound.
So we've kept you waiting long enough. Let's get down to business.
Are you ready?
I'm ready.
You mind if I flip the switch?
Go for it.
This is compact rocket sled in 3, 2, 1.
That didn't mess around.
No. That second stage was a hell of a thing. It was like, it just disappeared.
Now that was fast. Really fast.
That was unlike anything I've seen before. We've seen plenty of rocket launches. I'm used to speeding up of a rocket, but when the second stage kicked in, I was thinking, I've never seen anything go that fast. And then I realized, actually, that's correct. I have never seen anything go that fast. 3.
Awesome is such an overused word, but that truly inspired awe. And then some. Incredibly, the spectacle of the launch is matched by the destruction of the rocket's destination.
Wow, that's a lot flatter than the one out on the runway.
I wouldn't exactly call it flat. It's more like shrapnel.
What an impossibly large amount.
There's the 1-inch plate over there.
Yes, this twisted, folded, and all-around mangled piece of metal
Look at that.
was once a square piece of 1-inch thick steel plate.
I wouldn't have called this. It's a freaking potato chip.
For an encore of all.
Holy crap. This is even the car.
And an opportunity to crunch the crucial numbers, Adam and Jamie check out the aptly named high-speed footage.
I think we'll stop it there. I honestly don't even remember the full context of the myth that they're testing, but ridiculous, awesome, if you want to call it that. But I show this video because when I see things like this, it is page 5, by the way. When I see things like this, right, it brings up all those questions I feel like I had when I was young. Questions like, what makes things the way they are? Why do, materials have certain properties? So like, What makes some things stronger than others? What makes things soft or hard or light or heavy or skinny or sorry, shiny or durable or bendable or, whatever? What makes some things catch fire? What makes something a solid or a liquid or a gas, right? All these questions that I think we've all thought about from time to time, right? What makes up the world around us? It's a question that permeates all the way down to little kids. If you're a fan of Bluey, then you might recognize this clip. Oh shoot, it didn't play. There we go.
Okay. It's a bushweed. Yeah, man.
Is everything in the whole world made of atoms?
Yeah, I think so.
Well, is it? Is everything in the whole world made of atoms? Well, it is a question that humankind has been pondering for a long time. Among the first really recorded instances of humanity wondering and investigating, I guess you could call it that, what makes up matter, what makes up objects, materials, the world around us, goes back to the ancient Greeks, particularly a man named Democritus. And he's kind of given the nickname the laughing philosopher because for whatever reason, in all of these different paintings of him, he's smiling or laughing, and we don't really know why. But he's one of the first to really kind of document this idea of matter and it being made of smaller pieces, right? Everything we know of, even things that are solid, are in fact made of smaller pieces. And what's the nature of those smaller pieces? We're going to watch a short video here that really defines this term atom, A-T-O-M. What does that word mean? Why do we still use it today?
Our story begins in ancient Greece in 400 BC. At that time, man firmly believed that all things were composed of four basic elements: earth, air, water, and fire. But Democritus, a philosopher of that era, thought that these elements could be divided into smaller particles. In fact, he even gave them their name, atomos, which means indivisible.
I crumble this earth to soil, and in turn crumble this soil to dust. Now, if I could reduce this dust into its smallest particles, these would be atoms. This beach appears to be a solid carpet, but on closer inspection, we see that it is made of millions of grains of sand. If we think of grains of sand as atoms and pack them together, they can be molded into any desired form. So it is in this way nature uses these tiny particles, these atoms, to build all things: the earth, water, air, and fire.
So that's the gist of it, really. That's kind of the idea of what that word atom means. It comes from the Greek atomos, which means indivisible. And if that word, seems odd, you could think of it as uncuttable in a sense. Like the video talked about, if you took sand and you crumbled it to dust and you continued to divide something further and further and further, you would eventually reach a particle that itself cannot be cut or divided anymore. And so that's what that word atom means: an indivisible, uncuttable particle. And this again is a Greek idea. But the first person we're really going to talk about his name is John Dalton. And so this is on page 5, this section up here on John Dalton. And then on the next page, page 6, there's a question up here. So that's where we're going to be writing a few things down right now, is these two sections. John Dalton in the early 1800s kind of ran with this idea that the Greeks had. Not necessarily the earth, air, water, fire idea. He didn't believe that, but he did believe that all matter was composed of atoms, and these atoms were indivisible or uncuttable. And you can see here a rudimentary periodic table of sorts that he had made. That, again, he doesn't believe in the air, water, earth, fire, but he does believe that these atoms or these elements, these substances, are made of unique atoms. And so this is his periodic table. Let's watch a quick little summary of John Dalton.
John Dalton was an English chemist and physicist, best known for his work on atomic theory and his work on colour blindness. Dalton was born in Cockermouth on the west coast of England into a family of Quakers. He worked at a Quaker school until 1793 when he moved to Manchester. Dalton learned a great deal of his scientific knowledge from a blind philosopher named John Gough, and from this Dalton was made teacher of mathematics and philosophy at a college in Manchester until 1800, when he was forced to become a personal tutor due to lack of funds available at the college. Dalton began a meteorological diary in 1787 and made an estimated 200,000 weather observations during the remainder of his life. He also wrote a paper on the phenomenon of colour blindness, which had not been fully documented until Dalton's work was published. Daltonism became a common term for the condition at the time. He was then made secretary of the Manchester Literary and Philosophical Society in 1800, and in 1801 he published papers on the constitution of mixed gases, the pressure of gases at different temperatures, and the evaporation and expansion of gases. In 1808 he published a book called A New System of Chemical Philosophy. This was his groundbreaking work on atomic theory based on 5 propositions. The first proposition was that all matter is composed of extremely small indivisible particles called atoms. The second and third propositions state that atoms of each element are identical in size and mass, and that atoms cannot be created or destroyed. The fourth and fifth propositions are that elements combine to form chemical compounds in simple ratios, and that in chemical reactions atoms are combined, separated, or rearranged. He also published the first table of atomic weights, as well as his work System of Chemistry. Dalton also lectured at the Royal Institution in London and was awarded a fellowship in 1822. He never married and died in 1844 after suffering several strokes in the previous few years.
Okay. So in that video, it mentioned kind of 5 main propositions, 5 tenets of his atomic theory. And we're going to write those down on page 6, where it says, number 1, what is Dalton's atomic theory based on? Well, it's based on kind of a bit of a Greek idea of atoms, but really this is Dalton's atomic theory. And again, I want you to write this down on number 1 on page 6. So here are the first 3. Number 1 is everything is made of atoms. Everything. Every object, every material, every substance is made of atoms. Number 2, atoms are given of a given element are identical in size, mass, and properties. So clay is made of clay particles, clay atoms. Air is made of air atoms. Wood is made of wood atoms, and so on and so forth. Atoms cannot be broken down. Okay, and again, that's kind of the Greek idea that he's going with. The term atom literally means indivisible or uncuttable, and he subscribed to that idea. If you need a little more time to write these down, the sub can pause this video. If everybody's okay, I'm going to move on in 3, 2, 1. Number 4, atoms of different elements combine in simple whole number ratios to form chemical compounds. So for example, water. Water is not itself a pure element made of the same type of atom. It's made of different atoms that are combined in a whole number ratio. And then lastly, number 5, in chemical reactions, atoms are combined, separated, or rearranged, but are not destroyed. Okay? Atoms, whatever atoms you start with are the same atoms you're going to end with. They just look a little bit differently. Okay? Same thing, if you're not quite done yet, the sub can pause this video right now and let you finish writing this up. But otherwise, I'm going to move on. Okay, in this little square here on page 5, I want us to draw a picture. I want us to draw really what we think Dalton is describing when he says the word atom. And before we do that, right over here, I again want you to write down, what does the name atom imply about the structure of matter? Well, the word atom implies indivisible or uncuttable. So in this little box over here, what do you think you ought to draw? I want you to take maybe 30 seconds. You can write down over here what the term atom implies, and then I want you to tell your partner, what do you think John Dalton imagines an atom looks like? Okay, take about 30 seconds. I'm going to get my iPad ready so I can draw. Okay, hopefully you've got an idea, right? I'm thinking in my mind, I want to draw a ball, really, some kind of sphere but that sphere doesn't have any sort of internal structure. It's not made of smaller bits and parts or pieces. It's just an atom. So I'm going to draw a little sphere here. And you can kind of give it some three-dimensional qualities if you want to. So something like that. Maybe I'll try again really fast. Again, just a sphere that isn't made of anything smaller. It is indivisible. It is uncuttable. This is the Dalton atomic theory. And in addition, like if this example is a hydrogen atom, then an oxygen atom would be a little bit different in mass and in properties, but it itself is still uncuttable, indivisible. Should be a fairly easy drawing, I think. Okay. Let's move on a little bit in time. Again, that was John Dalton. He published his work on chemistry and atomic theory in, I believe it was 1808. So we're moving forward in time a little bit, about 100 years, give or take, to another man named J.J. Thomson. Okay. So again, you want to be on pages kind of 5 and 6 simultaneously, ready to write some things down. Let's talk about J.J. Thomson. What did J.J. Thomson discover that changed the way we think about atoms? Right? This is a picture of what's called a Crookes tube, and it demonstrates the experiment that J.J. Thomson conducted that radically changed the way we think about atoms. Sometimes it's called the cathode ray experiment. Okay? I'm going to show a brief video. This is a modern version of a Crookes tube, and we're going to see exactly what that Crookes tube does and how it demonstrates that maybe the atom is not exactly what John Dalton thought it was.
So today I'm at the University of Sydney with Dr. Phil Dooley, and we're talking about how our idea of the atom changed from a tiny little hard sphere to something more complicated. And this apparatus has something to do with that.
Exactly. It was quite a landmark historical experiment. It's just made of a tube of glass connected to a vacuum pump. And in the tube of glass, there are two pieces of metal connected to a high voltage power supply.
So we can suck the air out of here.
That's right.
And then apply high voltage to two metal plates.
Yes.
Okay.
Normally with high voltage in air, we don't get anything except maybe a big spark. But what Geisler found, who did this in 1857, was something quite different. So should we have a look?
Let's do it.
Okay, let's turn on the pump and the high volts. Turn off the lights so we can see what's going on. As you can see, something's happening now.
Yeah, I see a bit of a pink glow in there.
That's right. So imagine Geisler, the first person to ever see this. It's pretty surprising. That started people thinking, what is this stuff that's coming from the cathode? It seemed to be a ray emitted from this negatively charged one, which they called the cathodes. Therefore, it's called a cathode ray. And it became the topic for research for the next 40 years as all the big wigs of physics and science basically tried to work out what was going on.
So what did they figure out? I mean, what is going on? What's producing this this glow here?
There were two main camps. One thought that it was waves, and the second thought that the electricity was being carried by a stream of charged particles. Over the next 40 years, they basically came to the conclusion, well, it was J.J. Thomson in 1897 who came up with the idea that there is a stream of very small charged particles, negatively charged. They're smaller than an atom. So the smallest atom, hydrogen atom, they're about 1,000th of the size of that. And it doesn't matter what material the metal is, it's always the same particle. So this particle appears to be in everything. This electron, as it was known, is what's carrying the electricity.
So Thomson came to the conclusion that all atoms have this particle as one of their constituents.
That's right. So it wasn't a billiard ball. There had to be something inside the billiard ball.
So how do I picture like a billiard ball with bits inside it? I mean,
well, you should probably think about a pudding.
A pudding.
Yeah, well, that's what his idea was, that it was a plum pudding, very dear to every British person's heart.
Right.
That and inside the pudding you have plums,
and plums can come out of that. So when you apply high voltage, then a negatively charged electron, which Thomson pictured as a plum, comes out and leaves behind positively charged pudding.
Are you a fan of plum pudding?
For research purposes, definitely.
All right, well, let's see if we can research this a little further.
Okay, that sounds like fun.
Okay. So, how do you feel? You feel okay about that? Let me maybe show you a little computer diagram that might clear things up just a little bit. Let me see if I can zoom in just a little bit. Oh, that's not doing the right thing. There we go. So this is essentially what's going on. Again, there's a vacuum tube, so there's no air. We have these two metal plates that are applied to a high voltage, which is another way of saying a high energy electricity. What I'm going to do is I'm going to turn on the electricity by clicking on this check. And we can see that what happens is the electricity starts to pull something away from these metal plates. And then what happens is this thing that's being pulled out kind of goes through this little hole here. And then you can see right here, these are some charged plates. They have a charge on them. So what I'll do is I'll bring this slider here into the middle, and now there's no charge. And so you can see the beam just passes by. But as soon as I apply some charge, the beam is deflected. And so really what that told J.J. Thomson and others who conducted this experiment is that this beam of stuff, it's not a wave, but it is in fact a particle. Later, scientists would actually measure that this particle has mass. But the fact that the beam, these particles are deflected, what that tells us is that these particles have charge, electric charge. And you can see that they are deflected away from this negative plate and toward this positive plate. And if I move the slider over here and I make the bottom plate positive and the top plate negative, they are still bent toward the positive and away from the negative. Now, you've likely heard back in elementary school the phrase likes repel and opposites attract. Well, that is exactly what's going on here. Because this beam of little particles is attracted to this positive plate and repelled by the negative plate, what does that tell us about the charge of the beam of particles? It tells us that the beam of particles is negatively charged. And so this is really this groundbreaking discovery from J.J. Thomson, that the atom is not indivisible, like Dalton proposed and the Greeks proposed. The atom is not an indivisible, uncuttable sphere or ball. It is more complicated. It actually has internal structure. It is made of smaller pieces. So in this little box here on page 5, we want to draw a picture of this, okay? You can write down here, what was Thomson's major discovery? He discovered this negatively charged particle that makes up atoms, and he called it the electron. How did this change the model of the atom? Well, it told us that the atom is indeed made of smaller pieces, smaller bits. All right, what do we draw for that picture there? Well, like that professor said in that video, the name of this model that was given to J.J. Thomson's idea of an atom is called the plum pudding model. Now, back here on this slide, this is what plum pudding looks like. It's not actually pudding, it's like a cake, and these little bits are plums, or bits of plums. But this is kind of the idea of what an atom is. You've got this plum that is like an electron, a small little negatively charged particle. And then the pudding or the cake is the positively charged, you could call it matrix, the positively charged stuff. Because what a scientist knew is that, an atom itself is neutral. An atom itself doesn't have charge. So if we all of a sudden take an atom apart and find these little bits that are negatively charged coming out of the atom, well, then there also must be a positively charged part to balance out the negative part so that the whole atom is still neutral. So what you can draw is maybe something that looks like this. You still have kind of a sphere, some kind of ball-looking thing. The ball itself you could call positive, but inside the ball or inside the sphere are these little negatively charged electrons. So this is a common picture that you could draw. If plum pudding isn't easy for you to think about, you could think of it like a watermelon, right? The watermelon itself is the positively charged matrix, and these little seeds are the electrons that are kind of dispersed throughout. Here's another picture that you could draw. Okay. But pretty simple, really. But different, right? Right, like, and it's interesting, right? We're on our second model on this page, and already the term atom isn't really true anymore, right? The word atom means indivisible or uncuttable, and already we know that's not true. Atoms are not indivisible and uncuttable. They are made of smaller bits. Okay, right over here on page 6, I just want to make sure we get this one filled in. It says Thomson's cathode ray tube proved the existence of, and we can put electrons in that blank. It also proved that atoms are not, and then in this blank we can put uncuttable or indivisible, as Dalton proposed. Okay. All right, with that, we're ready to move on again. Fast forward a little bit, not like 100 years like last time, just a few years later. Enter into the scene a new scientist whose name is Ernest Rutherford. And Ernest Rutherford, like Thomson, is just conducting investigations, and he stumbles across something profound that he really wasn't looking for. I mentioned this, I think, last week, or maybe, no, it couldn't have been last week, earlier this week. A lot of times science kind of happens by accident. You just stumble across something. And that's the case here, as it was with J.J. Thomson. So let me show you a little computer simulation of what Ernest Rutherford found. So here is a plum pudding looking atom. It's something that Thomson would have drawn, Thomson thought about. And so to give you an introduction to Rutherford, what Rutherford is doing is Rutherford is conducting an experiment where he has a radioactive substance, and this radioactive substance is spontaneously emitting particles, charged, energized particles that are moving very fast. And he calls these particles alpha particles. Okay, so again, radioactive substance that's inside of this little thing over here, and that radioactive substance is emitting alpha particles. And so this basically, it's a box of lead, and inside that lead box is the radioactive substance. So the lead can protect us from those alpha particles, but there's a little hole right over here where the alpha particles can be ejected. And what Rutherford is trying to do is basically shoot these alpha particles at a very, very thin sheet of gold foil. That's his idea. That's what he's trying to do. And what he thinks should happen is, because J.J. Thomson's right? J.J. Thomson must be correct that this is what an atom looks like. What he expects to happen is when he fires these alpha particles at a plum pudding looking atom, what he expects is that these alpha particles will all pass through undeflected. Because what he imagines is, because the positive charge of this plum pudding is so spread out, that it's not enough to interact with these alpha particles. And so the alpha particles should just pass straight through, and nothing happens to them. That's what he expects to happen. Okay? But that is not what actually happens. What actually happens is something that looks more like this. So you can see here these alpha particles streaming through. You'll notice that most of them do pass through unscathed, right? Their trajectory is unaffected. But there are a few that are affected. You can see that some of them are deflected a little and kind of glance off at an angle, and others are deflected a lot, like sometimes 90 degrees, sometimes straight backward. The deflection is very, very significant. And this is surprising to Rutherford. Why would this happen? Why would a small number of these alpha particles be deflected? Some of them deflected at very large angles. What does that mean? Well, this is the conclusion that he comes to. That an atom is not like a plum pudding. It's not a spread out mass of positive with little bits of negative inside. Okay, you can write this down on page 6. Instead, Rutherford makes this ridiculous at the time, but true assumption that the atom itself is mostly empty. The space that an atom takes up, most of it is not filled with matter. It's mostly empty space. Most of the mass that makes up an atom is concentrated. It's not spread out like Thomson thought. It is concentrated in the center of the atom. That's where most of the mass is. And so that's why most of the alpha particles pass straight through. But some are deflected because they get close enough to this very, very concentrated mass at the center and essentially bounce off of it. It's a very different looking atom than the plum pudding atom. So let's fill in number 3 here on page 6. What are these 3 things that Dalton concludes from his gold foil experiment? Well, number 1 is that the positive charge is concentrated at the center of the atom. It is not spread out like Thomson proposed. Number 2, most of the mass of an atom is also concentrated in the center, not spread out. And third, and probably most importantly, the volume, the space an atom takes up is mostly empty. And you can roll with that idea and it makes your brain hurt. The chair you're sitting on is mostly empty space. The desk that is holding up your paper is mostly empty space. The pencil you're holding in your hand is mostly empty space. The paper that you're writing on is mostly empty space. The clothes on your back are mostly empty space. You, the atoms that make up your body, are mostly empty space. Everything is mostly empty space. It's a very strange thing to think about. Now, this diagram right here, let me make this full screen so we can see the magnitude of this. This diagram here does show, a concentrated part of the atom here in the middle. But even a diagram like this is wildly not drawn to scale. Let me show you exactly what I mean. If the volume occupied by an atom was the size of a football stadium, then the nucleus would be about the size of a blueberry. Think about that for a minute. If a football stadium is an atom, then the nucleus, right, that tiny amount of matter, of actual matter and positive charge, would be about the size of a blueberry. That's how much empty space we're talking about. It's a strange thought, but that's the conclusion we have to draw. So let's draw another picture. We have to include a few more things here. Let me get my iPad ready so I can draw with you. Okay, if we go back up here to the Dalton model, we can place little check marks on these little blue lines here. Like if we think about the Dalton model, these are all different parts of an atom that we are now familiar with. Did Dalton have any of these in his atomic model? No, he didn't. He just had an indivisible sphere. So I'm not going to put a check next to any of those. Next to the Thomson model, I can put a check next to electrons. Okay. Thomson discovered the electron. He discovered that an atom is not indivisible, but he didn't have any of this other stuff. Ernest Rutherford now has electrons as part of his model because he knew about Thomson's discovery, but he also introduces this idea of a nucleus. This idea that the mass of an atom and the positive charge is not evenly spread out. It is concentrated in the center, and that concentrated center is what he called a nucleus. Okay, we can also put a check mark next to this proton, right? Proton is really what Rutherford describes as the positive particles that make up an atom, but they're all concentrated in the center. Okay, right over here, what was Rutherford's major discovery? Again, most of the atom is empty space. And really all of the matter, all of the mass is in the nucleus. So what do we draw? Well, we can kind of draw something like this, some kind of, dotted line representing this atom is taking up space. but most of that space is empty. All of the matter is located in the center. So you can draw a dot in the middle, but a small dot, a dot that's big enough to see, but a small one, right? And even this diagram, like we just saw, is way out of scale. If this circle that I just drew were the size of an atom, the nucleus would be invisible. It'd be so small I couldn't see it. This nucleus is so small compared to the size of the atom. Yeah, a lot to digest, but that's the situation we find ourselves in. Okay, one more thing to show you before I let you work on the computer simulation activity for the remainder of the hour. And that is, what else makes up the mass of an atom? Okay, you can see here that one of these options that we haven't checked off yet is called a neutron. Well, after Rutherford, another scientist by the name of James Chadwick discovered another part of the nucleus that made up the atom, but wasn't discovered yet by Rutherford or by Thomson. And James Chadwick conducted a similar experiment actually to Rutherford. He had a radioactive substance in here, and that radioactive substance emitted alpha particles, and those alpha particles were bombarded at a thin sheet of a different element this time called beryllium. But what Chadwick found was that when those alpha particles struck the beryllium, a massive particle, meaning a particle that has mass, was ejected from the beryllium. But unlike Rutherford and unlike Thomson, when Chadwick put charged plates on either side, what he found was these particles that were ejected from the beryllium were not affected at all by these charged plates. They passed by undeflected, unscathed. And so what that led him to believe was these particles, they do have mass, but they do not have any charge. And that is why he named them neutrons. Neutron having that prefix NEU, meaning neutral. These particles don't have charge anymore. And so if we go back here really quickly, now we really know 3 crucial facts about an atom. Most of the atom is empty space. Okay. Most of the mass of an atom is concentrated in the center in what we call the nucleus. The nucleus is where we're going to find these particles called protons and neutrons. Okay. And then that third element, the one that Thomson discovered called the electron, that is also part of the atom. And so at this point, I think you're ready to start. You clearly are not going to finish this activity today, and we'll finish it up Monday, which is totally according to plan. But I'd like you to get started, okay? When the video ends, you and your partner are going to go get a Chromebook. And I'm trying to think. I think I would like everybody to have their own Chromebook. I do want you to work as a pair and talk to each other, but I'd like everyone to have their own Chromebook so you can see this for yourself. All I want you to really do is go to page 7, and I want you to start following the instructions. I think the instructions are very simple and very easy to follow, so I'm hoping you don't get lost. But if you do, that's why you're working together. You can ask, you could get some help. It's not that hard. But I want you to get started, okay? Work your way through, and it's pages 7 through 9. It goes all the way through page 9. Follow the instructions and see what you find. See what you find out about atoms, their structure, and really how we identify them. That's kind of the point of the activity. Yeah, that's about it. I hope you enjoy the activity. Just work until the bell. When the bell rings, then you can put away your Chromebooks, and I will see you on Monday. Have an excellent weekend. Thanks.